In this video, I want to look at differential equations. So, a differential equation is one of which that you're solving for an unknown function. We usually call this function y equals f of x. And usually a typical example could be, like if you have, for example, like y prime is equal to, let's say x squared. Okay. So for this would be an example of a differential equation. And your goal would be that you want to solve for that differential equation. But the method of which that you would need to solve for this is that you would need to basically rewrite the differential as dy dx, or the derivative as dy dx is equal to x squared. And then from there, you would need to separate the variables, because basically this type of equation is what is known as separable, meaning that we can isolate the respective variables and then solve individually. So we could say, like, for example, you have dy equals to x squared, and then you have dx. But then how do you solve this? You have to integrate on both sides. So you integrate, and what you get is that this gives you the equation y equals to x cubed over 3, and then plus some arbitrary constant. So we have that basically our solution to the first order differential equation is the cubic function 1/3 x cubed plus c. Now, if, for example, you had an initial value, such as, like, for example, if you have that when you plug in the value of 3, that it gives you equal to 6. Well, in any case, you could solve that algebraically by substituting how you have 3 cubed divided by 3 plus c, but we know that basically that the value of which it should be is 6. So you would have 6. But then that tells you that you end up with the following: 27 divided by 3 plus your constant is equal to 6. But notice that this is going to be 9, so you have 9 plus c equals to 6, which then tells you that c equals to minus 3. So we have here that a solution would be y equals 1/3 x cubed minus 3. Now, you might be wondering, what is the difference between the two? And the difference between the two is that essentially one represents a general solution, x cubed divided by 3 plus c, and the other represents a particular solution. So we could probably just label one as a general, and then the other as a particular. Now, in this case, this was us just solving a differential equations via substitution, well, separation of variables, that is. And one way that you can think of a differential equation is by just thinking of the rate of change, for example. You learned that at some point that the dy dx is equal to the derivative, which in any case, you have that y equals to f prime of x dx. But how do you solve this? Well, you have to integrate. So you end up with y equals to f of x, and that's plus c. This is probably the simplest differential equation that we can work with in any case. But another thing that you could do is, for example, how do we come up with differential equations? So one way is that, for instance, suppose that you had a function, and let's say that that function is e to the 2x. But then let's say that the equation is also added to e to the 3x. So one way that I can derive an equation we take the derivative, so we have 2e to the 2x, and then we have plus 3e to the 3x. But what if I was to basically say, well, take the second derivative, and now I have 6e to the 2x. Actually, it's not 6, is it? Should be 4. So I have 4e to the 2x plus 9e to the 3x. Now, notice here that if I was to basically multiply the first equation by 5, I would get 5y equals to 5e to the 2x plus 5e to the 3x. But then what if I was to, let's say, for example, multiply the second equation by minus 5. So let's say we multiply that by minus 5. We get minus 5y prime equals to negative 10e to the 2x. And then we have minus 15e to the negative 3x. But what happens when we add these two? Well, what happens when we add these two, basically we have minus 5y prime plus 5y equals to negative 5y, negative 5e to the 2x, and then we have a negative 10. So here we have a negative 10e to the 3x. Now, in any case, our goal would be to probably try to reduce this as best as possible so that it could equal to 0, for example. Now, what if from here we added another y? So we add another y to this equation. So that's going to be y equals to e to the 2x, and then we have plus e to the 3x. So what happens is that you end up with the following. You end up with minus 5y prime plus 5y, not 5y because we added an extra, so 6y equals to, well, that's going to give us negative 4e to the 2x, and then we have minus 9e to the 3x. Now it looks that I have actually, on the right-hand side, it looks that I have minus the second derivative. So I have minus the second derivative, which in this case, we can then go ahead and rewrite it by just moving this to the other side. So we have now a second-order differential equation with the solutions of e to the 2x and e to the 3x. Now note in this case, this is a particular solution, but we have that the solution to this differential equation that we just constructed, it's actually going to be y equals to c1 e to the 2x plus c2 e to the 3x, where c1 and c2 are arbitrary constants. In any case, we were more or less just deriving the differential equation from the exponential equations e to the 2x and e to the 3x. Now, of course, if we wanted to verify this, we could just take the derivative of this equation once and twice and plug it in. So what that means is that, for example, if you have a differential equation that is of the form y double plus, let's say, a y prime plus by, and this is all equal to 0, in actuality, whenever you're trying to solve this, your differential equation will actually be of the form e to the rx in any case. So that means that if you have a second-order differential equation of this form, you do not need to do anything beyond just substitution. because, take for example, y double plus 7y plus 12, that's a y prime, y equals to 0. So we take the derivative of this equation, which is re to the rx. But we take the second derivative, and we find that it's going to be y double equals to r squared e to the rx. Now if you plug that in, you have r squared e to the rx plus 7r e to the rx plus 12 e to the rx equals to 0. Note that the e to the rx is a common factor multiplied by r squared plus 7r plus 12 equals to 0. Now, because an exponential function is always non-negative, we have that r squared plus 7r plus 12 equals to 0 can be factored as r plus 4 and r plus 3 equals to 0. But this would mean that r equals to negative 3 and negative 4. So in this case, I have basically my solution, because it's telling me that the second order differential equation, it has the solution set such that e is raised to the negative 3x and e is equal to, or the second one is e to the negative 4x as our independent set solutions. So y equals to c1 e to the minus 3x plus c2 e to the minus 4x. This would be our general solution, which of course if we wanted to find a particular solution, we would need an initial value in actuality. So if we were told, like what is y of 0, what is y prime of 0, we could actually solve these using a little bit of linear algebra in either case. Now, suppose that you just wanted to verify whether or not a differential equation can be satisfied with a proposed solution. So the classic example could be if you have y double plus 4y equals to 0, you can verify this via suppose that the equation was cosine of 2x. Well, y prime equals to negative 2 sine 2x, but y double is equal to negative 4 cosine of 2x. This means that if I substitute y double with minus 4 cosine of 2x, and I add it to 4 times cosine of 2x, this equals to 0, which in either case you can tell that you'll get 0 equals 0, which is actually a true statement. Now, let's say that you wanted to basically solve a differential equation presented in a particular form. Now, most differential equations can be solved as long as you can isolate the differential dy, or in either case, whatever the respective variable would be. So let's say that you have a derivative, so dy, and it's equal to basically a product of two functions, like f of x and g of y. But let's say that this was divided by dx, right? So if I can separate the two functions respectively as follows, where I have dy is divided by g of y, and this is equal to, basically we have f of x times dx, then in any case, yes, you can integrate both sides and solve for the respective unknown function, that is. So in actuality, that means that basically every single integration problem that you have seen leading from Calculus 1 to Cal 2 is basically could be considered as a differential equation, essentially. But in any case, like let's say, for example, that you have dy over dx is equal to, let's say, 2xy, and then let's say that this was divided by x squared plus 1. Well, notice that in any case, it's very not too bad to separate the variables such that you can rewrite it as dy over y equals to 2x over x squared plus 1. But then you have the differential dx. So always the next step would be the integration. So you have the integral, and basically you end up with the natural log of y, and then this equals to, similarly, you have that this would equal the, by u substitution, that would be also the natural log. In this case, it would be the natural log of u. And then you have this is plus c. Now, in any case, what do you need to do with the u is to plug it back in. So you have natural log of x squared plus 1 plus c, and then you have the natural log of the absolute value of y. Now, from here, though, how would you solve this? You would basically just take the e on both sides. So the easiest way to do this is just to say that you take e and you raise it so that basically from here you can rewrite this as the absolute value of y equals to, okay, well, notice that it has an arbitrary constant. It has e raised to a c. So we can just write that as e to the c. But then notice also here that this cancels out, giving you just x squared plus 1. Now, in any case, notice here that the y, the absolute value of y, equals plus or minus. So that's going to be y equals to plus or minus e to the c times x squared plus 1. Now, the only thing, though, is that the e to the c is an arbitrary constant nonetheless. You have e to the c is just another constant. Interestingly enough, this tells us that the solution to our separable differential equation is y equals to the arbitrary constant multiplied by x squared plus 1, and then we have it. So here we have that this gave us the solution. Note that if you, for instance, took the derivative, you could also derive the equation in any case. But to do that, you would have to probably solve for c in either case. Now, one thing, though, that you could look at, for example, is what happens when you have an initial value problem. So an initial value problem is one of which that you have a differential equation. So let's say that you have a differential equation, dy dx equals to e to the x minus y. But you're given an initial condition, which this initial condition will say that y of 0 is the natural log of 3. Now, in any case, this can be solved easily by simply just separating the variables. Because notice that e to the x minus y is the same thing as e to the x divided by e to the y. Well, from there, you can easily see that the variables could be separated such that you have dy and you have e to the y is equal to e to the x, and you have dx. Now be careful with this because we're not necessarily saying that both x and y are equal, but let's see. If we take the integral, what does that give us? Well, it gives you that you have e to the y equals to e to the x but plus c. Now, notice that here we can get the the y by itself because y equals to the natural log of e to the x plus c. But then what could you do? You plug in 0, so that's going to be natural log of 1 plus c. But we know that that was equal to ln of 3, which in any case would imply that 1 plus c equals to 3, so c equals to 2. From there, now we have our general solution. Our general solution says that y of x is equal to the natural log of e to the x plus 2, and then we have it. So this is our solution to our first order separable differential equation. Now, one thing that you should take away from learning the basics of differential equations is that a differential equation can be used for real life situations or real world applications in terms of mathematical modeling. So if you are looking at the rate of change that just so happens to be directly proportional to the present, that would be a differential equation. If you're looking at the rate of change that is equivalent to the difference of temperatures, that's a differential equation. If you were looking at, say, for example, an infectious disease, you can technically model it by saying, well, what if I had an equation that represented the amount of people that were sick, and we said that the rate of change is a direct proportion to those that might be sick and those that are not sick. But if that's the case, then you have to have a population. So like you could say like M is a population. Well, in that case, that would be M minus the population. And in this case, now you have basically a first order separable differential equation, of which in solving for this, you would have to basically separate the variables in either case. So here is an example of which that you can try. You can try where you have that the population is equal to, let's say, like 50,000. But then let's say that the initial, which is going to be at 0, you had that there was 100 people that were feeling sick or infected, that is. But then let's say that after, let's say like 2 weeks, so like 14 days, you have that perhaps, let's say like 2,000 people became sick. Then in that case, you can solve for the equation that describes the spread of this disease in either case. How? Well, for that, you would have to basically take the derivative. You would say that it equals to some unknown constant, call it k, multiply that by the 50,000 minus the population. Actually, not the population, but the amount of people that were sick, multiplied by the population, the people that are sick in this case. So how do you solve this? Well, in this case, it would be a separation of variables where you have that dy is divided by 50,000 minus p, but then this is times p, and this equals to k, and that's dt. Now notice that here you can solve this differential equation. But for this would equal to naturally the kt plus c. But then how do you solve this one on the right-hand side? The one on the right-hand side represents basically a partial fraction decomposition, which would then say that you would have to figure out what is a over 50,000 minus p plus b over p, and this has to equal to basically 1 over 50,000 minus p, but also times p. Now, in any case, for example, if you were to, let's say, figure out your go-to method of partial fraction decomposition, you should figure out that from here, that, for example, that a is going to be equal to 1 over 50,000. And then from there, you'll see that if you have the b, or like if you are going to solve for b, basically you're going to find that that is also going to be 1 over 50,000. Now in that case, that means that now that you can integrate these two because you've found the unknown constants. And from there, once you find your equation, you're going to use that the amount of time that has passed in 2 weeks, that it went from 100 to 2000. And it's going to basically give you what that equation is going to look like. In either case, once you have completed finding the solution, that is, you're going to find that the equation defines basically a logistic one, where you have a equation would be that you have like a over 1 plus b, and then you have e to the ct. This would be how the equation should come up. But for this one, you would have to figure out, what is the a, what is the b, and what is the c, for example. And yes, it does seem like we have too many unknowns in that case, of which is true. But more or less, like once you solve for the equation itself, you will be able to describe the length of term of this particular disease and like what its peaks would be in that case, which is really just 1, which is kind of like the halfway, where you have that half of that population, once it's been overtaken, that's where the rate of change begins to slow down, basically. And if we look at its second derivative, that is, we'll be able to see that for the, well, not the second derivative, but the first derivative. The second derivative just describes like the length of the length of time that it takes to slow down. But the first derivative, the first derivative, that you will see that it kind of resembles a bell curve, if you will. So when you graph it, once you find your equation that corresponds to these parameters, you'll see that that graph, it looks something like this, of which you want to figure out exactly where that halfway point is in either case, because it would allow us to basically determine things like, how long would it take before we have that it's reached its peak, which means how long do we have until we could perhaps come up with a vaccine, come up with a plan, isolate the city, and those kinds of things. So we can do that. And to do that is by basically using a differential equations, which in any case, something like this, yes, is a little challenging, but it can be also solved, in a sense, numerically. Because in either case, we have the conditions set. So, in a sense, that equality holds very strongly, of which that you could basically just approximate your values for p, or values such that you can find basically a solution. But that solution, in any case, is obtainable for something like this.